Hello students, welcome to Educate. Today we are going to study equipotential surfaces. Surfaces that have same potential. Suppose here there is a charge. Suppose charge is here and at distance r here if you find potential. So V will be equal to Q upon 4 pi epsilon naught r. If you find this is a point P, say this is point Q. So here if you find potential, distance is same. If you find potential here, still distance is same, so potential will remain same. So this is surface where potential is same. Similarly, if you consider another surface at distance say capital R from center, here at center charge is say small q. So here if you find potential on this surface, you will see that it is constant throughout. Similarly, if you consider another surface, here also potential will be same. So such surfaces where potentials are same are called equipotential surfaces. So here if you move any charge from this point to this point, will there be some work or not? So what is formula for work? So work equal to, if you remember the definition of potential, when we define potential we say work divided by charge. Here our concern is to find work, so potential into charge. In this case, suppose we take potential here V and this separation is R from charge. So here potential is V. At this point if you take potential will also be V. So if you find potential difference, in place of V you write delta V into Q. Since delta V, this is equipotential surface, so delta V will be 0. So what you have got? Work done in moving any charge on equipotential surface is 0. Now different types of equipotential surfaces are possible. Here these are equipotential surfaces. So if you make it bigger, you will see that this is uniform electric field. So these are equipotential surfaces. So for uniform field, equipotential surfaces will look like this. Now if we observe what will be the shape of equipotential surface for positive and negative charge, so it will look like this. You have to practice. And suppose both charges are of same nature, in that case equipotential surfaces will look like this. Now here two equipotential surfaces are shown and we have to find out. If you remember that electric field is minus dV upon dr. What does this mean? Potential gradient, negative gradient potential is equal to electric field. It implies that potential decreases in the direction of electric field. Suppose here there is positive charge Q and if you find potential here, suppose at point A, then at point B, since it is positive charge, so electric field will be like this. So at this point potential is VA, at this point potential is VB. So if you find the difference VB minus VA, so you will get negative. It means potential is decreasing in the direction of electric field. So you can say that electric field is negative gradient of potential. Here some points are given that you can read. Electric field is in the direction in which the potential decreases steepest. As I have shown you that in the direction of electric field, potential will keep on decreasing. Its magnitude is given by the change in magnitude of potential per unit displacement normal to the equipotential surface at that point. This is the same thing as I told you. Now, we are going to see potential energy due to single charge and due to system of charges. So, different situations we will see, like suppose at this point potential is V and you bring a charge Q, then what will be potential energy? If we denote potential energy as U, so it will be equal to V times Q. And suppose there are two charges, then what will be potential energy? Suppose there is system of charges here. This is charge Q1, this is charge Q2, and the separation between them is R12. In that case, what will be potential energy? So we can denote potential energy as U. So U will be Q1 Q2 divided by 4 pi epsilon naught R12. If you have question why, so it is simple. Do one thing. Suppose at this point you have to find out potential energy. So consider potential due to this charge at this point and then multiply by this charge. So potential at this point due to this charge will be, say, we write here Q2 is equal to Q2 divided by 4 pi epsilon naught R12. Now you are bringing charge Q1 to this point, so potential energy will be equal to VQ2 into Q1, and VQ2 is this. So you can say it is Q1 Q2 divided by 4 pi epsilon naught R12. So this is case when there are two charges. Suppose there are three charges, then what will happen? So in case of three charges, suppose one charge is here Q1, this is Q2 and this is Q3. So what do you do? Suppose this separation is X, this separation is Y, this separation is Z, or you can also write R1 to R2, 3, etc. So here if you find potential energy, so say U is potential energy, so that will be equal to Q1 Q2 divided by 4 pi epsilon naught, and then separation is X. Then we take next two charges. So here Q2 Q3 divided by 4 pi epsilon naught, then Y. Then we take Q1 Q3 divided by 4 pi epsilon naught Z. So this is how we can find potential energy. Here you have to keep in mind that sign of charge must be taken into consideration. If any charge is negative, so you have to write it with the sign, because potential energy is also a scalar quantity. Now suppose there are four charges. So what is expression for potential energy? So if four charges are there, suppose this is one charge here, this is Q1, this is Q2, this is Q3, and this is Q4. And suppose this separation is R12, here this is R23, this is R34, this is R14, and then diagonal distance will also be needed. Keep in mind. So suppose this is R13 and this is R24. Now what you do? Just find potential energy. You will be all possible interactions. So Q1, Q2, 1 upon 4 pi epsilon naught will be common to all. So let's write them outside. Let's write it outside, and then we write Q1, Q2 divided by, what is separation? R12. Then Q2, Q3 divided by R23. Then Q3, Q4 divided by R34. Then Q1, Q4 divided by R14 plus, now this Q1, Q3 divided by R13 plus this Q2 Q4 divided by R24. So this is expression for potential energy due to four charges if they are located at the corners of a rectangle or any quadrilateral. If they are along the same line, then separately you can find. Then these interactions will not be there. That situation we can see, although such questions are never asked. Suppose here charge Q1 is here, then Q2 is here, then Q3 is here, then Q4 is here. Then how to find potential energy? So all interactions can be considered separately. So at which point you want to find out potential energy? That depends. Suppose at this point you want to find potential energy, then you have to consider potentials due to these three charges separately, and suppose combined potential at point, this is, say, V is V2 plus V4 plus V2 plus V3 plus V4. This is combined effect of potential at point this, and this separation, suppose this is X, this separation is, say, Y, and this separation is, say, Z. So first of all we have to find out what is potential. So V2 will be Q2 divided by 4 pi epsilon naught X plus Q3 divided by 4 pi epsilon naught Y plus Q4 divided by 4 pi epsilon naught Z. Now what you have to do? You have to find out potential energy at this point. So you are bringing that charge where potential is this much. So potential energy will be Q1 times V, and V is this, so you can write, so you will get potential energy. Now consider another case when there is a source charge somewhere here. There is a source charge, and due to this source charge, due to this source charge, at this point, say, potential is V1, and at this point, say, potential is V2. Now what you are doing, you are bringing a charge from infinity to this point, say Q1. So what will be potential energy at this point? So it will be V1 Q1. Now another charge you have brought to this point, say Q2. So potential energy at this point will be V2 Q2. So what will be total potential energy? So potential energy in this case will be Q1 times V1 plus Q2 times V2 plus interaction between these two charges. If suppose this separation is, say, R12, then there will be another term, and that will be Q1 Q2 divided by 4 pi epsilon naught R12. So this is expression of kinetic energy when two charges are there in the field produced by any source charge, where different potentials are there, where charges are brought from infinity. So you have understood this concept. Now these all situations are given here. Here is one question. Let's analyze it. Four charges are arranged at the corners of a square ABCD upside D as shown. Find the work required to put together this arrangement. A charge Q0 is brought to the center E of the square. The four charges being held fixed at its corners. How much extra work is needed to do this? So first of all, what we have to do is to find what is the potential energy of the system. And then as far as work done in bringing this charge here is concerned, so that can be solved by finding potential at this point due to these four charges, and then you can multiply by the charge to be brought. So that can be solved easily. Let's analyze, let's find out the potential energy of the system. So potential energy of the system will be how much? Potential energy U will be all interactions if you take these two interactions together. So 1 upon 4 pi epsilon naught you can take common, and then you write this, so minus q square divided by separation is D. Then next question, next part, interaction of these two will again give minus q square divided by separation is D. Then interaction between these two will also be minus q square divided by D. Then interaction between these two is minus q square divided by D. Now, what more interactions are possible? Here, these two will also interact. So, we will get q square divided by, this is d root 2, y d root 2, this is d, this is d, this angle is 90 degrees. So, diagonal. Similarly, interaction between these two will also give q square divided by d root 2. So, this is potential energy. Now, our question is, next part of the question is, a charge q0 is brought to the center E of the square, the four charges being held fixed at its corner. How much extra work is needed to do this? So extra work can be calculated by finding potential at this point and then multiplying that result by q0. So let's see the potential at this point. Due to this, potential will be how much? So here this separation will be how much? Here we can see this is D, this is D, so this will be D root 2. And if you take its center, it will be D upon root 2. So D upon root 2. So potential will be Q divided by 4 pi epsilon naught, we take outside, and then potential due to this charge, it will be 1 upon d root 2. Then if you are taking this charge, so minus 1 upon d root 2. Then if you take this charge, so plus 1 upon d root 2. And if you are considering this charge, minus 1 upon d root 2. So it will become 0. So there is no potential. Since there is no potential, so if you are bringing any charge, so no work will be done. So here result is given as I told you. Now further, potential energy of single charge, I have told you, if potential is given, then you have to multiply by it to get the result. And the potential energy due to two charges also we have studied. Then we have studied that if there is external field and the two charges are brought, in that case what will be the potential energy. So this relation we have studied, q times voltage at that point plus q2 times voltage at that point, then interaction. Now there is one question here. Determine the electrostatic potential energy of a system consisting of two charges with no external field placed at these two locations respectively, and how much work is required to separate the two charges infinitely away from each other. It means whatever potential energy they possess, so equal to that but of opposite sign. So now let's consider this question. So there is one more part of the question. Suppose that the same system of charges is now placed in an external field E equal to A upon R square, where value of A is given, what would be the electrostatic energy of the configuration? So let's consider the first case when charges are given and separation is given. So if you see the question, you will see that the positions are on here minus 9 cm and here another is 9 cm. So on number line, minus 9 to plus 9 will be 18 centimeter. So distance is 18 centimeter and the charges are 7 microcoulomb and minus 2 microcoulomb. So we can easily evaluate it. So let's do the evaluation process. So here we can write potential energy will be equal to Q1 Q2 divided by 4 pi epsilon naught times separation, say R. So one charge is positive, another charge is negative. One charge is 7 microcoulomb, 7 into 10 to the power minus 12, minus 6, and another charge is minus 6. Another charge is minus 2 microcoulomb, 10 power minus 6. 1 upon 4 pi epsilon naught will give 9 into 10 to the power 9 divided by separation is 18 centimeters, so 0.18 meter. Now we evaluate it, so it comes out to be minus 0.7 joule. So there is no doubt. Now they are saying that if you are taking them infinite apart, then what work is to be done? So the same amount of energy should be given so that potential energy becomes 0. So if you add, like you have minus 0.7 and if you give 0.7 joule energy, so total energy will be 0 and then body means the charges will be free to move. So that situation they have asked. Then next point is there is external field. In external field you have to find out potential energy. So location is already given that minus 9 centimeter plus 9 centimeter and relation is given that E is related to R, like here they are saying that E equal to E equals A is 9 into 10 to the power 5 divided by R square. Now we can evaluate it by putting the value of this is electric field. Now we can get potential. So relation for potential will be what? So relation for potential will be I had 2 points. First, let's find out the potential energy at first point where charge Q1 is there and the potential at that point is say V1, and another point say charge Q2 is there and the potential at that point is V2, and then their interactions should also be considered. So it should be Q1 Q2 divided by 4 pi epsilon naught and their separation R12. But here what is potential? So we are given E equal to, in our question here, A upon R square, and if you remember E equal to V upon R or E into R will give V. So we can reduce one R from here to get V. So V equal to A upon R, right, in magnitude. So here we can write A upon R, here also we write A upon R. So we can put those values and then we can evaluate. So A is given and potential is also given. So we can evaluate now. So thing is easier, don't worry, it can be done. Now, So we evaluate. So A times, here we need Q1 times V1 plus Q2 times V2, because interaction we have already evaluated as minus 0.7 joule. So later on that we will add. So here Q1, so charge is 1 is 7 into 10 to the power minus 6, and voltage formula, as per formula. So what is formula? A upon R. So A upon R is 0.09, because it was 9 centimeter. Here we are taking just magnitude of distance. And the second one, charge is minus 2 into 10 to the power minus 6 into voltage, that is A upon R, 0.09. So we can evaluate it, and we can put the value of R also, A also. So A is given 9 into 10 power 5. So 7 into 10 powers by the 6 into 9 into 10 to the power 5 divided by 0.09 minus this 2 into 10 power minus 6 into 9 into 10 to the power 5 sorry, divided by 0.09. So we evaluate it. So this will come out to be 70, this will come out to be 20. So this is 50. So we have got 50 joule, and the interaction of the two charges gave energy, potential energy, as minus 0.7 joule. So total energy of the system will be equal to 50 minus 0.7. So it will become 49.3 joule. So I think you have understood. Now, potential energy of a dipole in electric field. So let's see, you are given uniform electric field, and there is a dipole here making angle theta. So this angle is theta, length of dipole is 2a, here there is positive charge plus q, and here there is negative charge. Now we have to find out what is the energy. So we know torque is force. So in this direction force will be QE, in this direction force will be minus QE. So torque will be force into perpendicular distance. What is perpendicular distance? This one I'm drawing here. So this is 2a, this angle is theta, and this is perpendicular distance. So this will be 2a sine theta. So we can use it here. Force is QE times 2a sine theta, which can also be written as 2a into q is p. So PE sine theta. So this is torque. Now suppose a dipole is rotated through certain angle. So suppose initial angle is theta 1 and final angle is theta 2. So we can find the work done. So work done will be integration here, theta 1 to theta 2, and then q we can write PE sine theta and d theta. If you remember, I told you that integration sine x dx gives minus cos x. So here this will become, this is PE and minus cos theta and limits theta 1 to theta 2. So you can put the limits minus PE and cos theta 2 minus cos theta 1. Now here you can do some assumptions, like initially dipole was perpendicular, means theta 1 was 90 degree, and suppose it is brought to a position theta. So second term here, theta 1 cos 90 degree, that will become 0, and here we are putting theta. So we will be left with W work done equal to minus PE cos theta, and this work done equal to potential energy. So we have got the expression of potential energy. If we want to write it in here, since cos theta is involved, and if you remember AB cos theta is given, so you can write it A dot B. Similarly, you can write it as minus P dot E. So dot product of dipole moment and electric field, and with a negative sign, is equal to potential energy of a dipole in a uniform electric field. Now let's consider a numerical based on it. The numerical says, let's read it. The numerical is: a molecule of substance has a permanent electric dipole moment of magnitude 10 power minus 29 coulomb meter. A mole of this substance is polarized at a low temperature by applying a strong electrostatic field of magnitude 10 power 6 volt per meter. The direction of the field is suddenly changed by an angle of 60 degrees. Estimate the heat released by the substance in aligning its dipole along the new direction of the field. For simplicity, assume 100% polarization of the sample. So here situation is shown. So you will evaluate potential energy when theta equal to 0 degree. So that is initial potential energy. Now it is rotated through 60 degree. Then again you will calculate potential energy, and then you will find out the difference, and that difference will be equal to energy released. So here dipole moment of dipole moment is given 10 power minus 29 coulomb meter for one molecule. So dipole moment for one molecule, say P, equal to 10 power minus 29 coulomb meter, and here we are taking 1 mole. It is given field magnitude, the direction of the field is suddenly changed. Sorry, here it's given a molecule of a substance has a permanent dipole moment of this much, a mole of this substance. So you are taking 1 mole. So it means number of molecules will be equal to that of Avogadro number. Say it is 6.022 into 10 power 23. So just take 6 into 10 power 23. So total dipole moment, if we find, say it is P total, so it will be equal to number of molecules, like 6 into 10 to the power 23 multiplied by dipole moment of each molecule minus 29. So this will become 6 into 10 to the power minus 6 and coulomb meter. So we have got total dipole moment, and now situation is shown that this is direction of electric field. Initially dipole is like this, but later on its direction is changed like this. So in two cases we have to find out potential energy. So in first case, U1 equal to just PE, because theta is 0 degree with a negative sign. So we put the value minus 6 into 10 to the power minus 6 into strength of electric field, that is 10 power 6. So this gives minus 6 volt. Sorry, it's energy, it can't be volt, it's minus 6 joule. And then when it is at 60 degrees, so again we find potential energy. So that will be equal to PE cos 60 degree with negative sign, PE cos 60 degree. So it will be here 6 into 10 to the power minus 3 into 10 power 6 into cos 60 is half. So this will give minus 3 joule. So difference of the two. So you can evaluate final potential energy minus initial potential energy. So that will be work done or heat, you can say. So heat equal to U2 minus U1. U2 is minus 3 and U1 is minus 6. So plus 6 will give 3 joule. So there is loss in potential energy, and this must be energy released by the substance in the form of heat in aligning its dipole. So this is all for today. In next class we will study electrostatics of conductors, and here the properties of conductors, like inside a conductor electrostatic field is zero. So these are all things we will analyze. And next point is electrostatic shielding. Then we will see some questions, and after that dielectrics and polarization. Then after that there is capacitance and its different type of combinations, like parallel and series combinations. Then we will study energy stored and energy loss in sharing, and that will be the end of the chapter. Thank you for watching. Team Educate.